right now. There's some installation instructions. All you need to do is run pip install -r requirements.txt, and we should have all the requirements downloaded. One other thing you'll need is to download the Spacey language model. So the instructions are here for if you're on Windows or if you're on a Mac or Linux. But you know, either as admin or with sudo access, if you run the command python-m Spacey download en. And what this will do is it will download the English language model, which we will use for tokenization. And again, I understand you guys might not understand that, but by the end of this lecture, you will understand what those terms mean. Okay, so here's what we plan to cover in this particular workshop. So we're going to start out by giving a brief overview of the history of NLP and how we can get our computers to represent our language data. We're then going to look at something called distributed representations. Following that, we're going to look at two critical concepts in NLP, preprocessing and tokenization. Basically, how do you go from raw text data to something which we can give to a computer? And then we're going to look at Word2Vec, which is an implementation of distributed representations, and specifically the skipgram model. And then we're going to look at Spacey, which is a industrial level tool to facilitate the pre-processing pipeline. Over the course of this particular workshop, everything that I said will become clear. I can understand how, you know, hearing distributed representations does feel like you're suddenly thrown straight into the deep end of the pool, but I promise you it's not going to be like that. This is going to be a very, very gentle introduction. Okay, cool. Okay, so just to provide a brief overview of the history of NLP, this isn't something that I want to spend too long discussing, actually, because, you know, we're here to learn some cool stuff. We're here to learn neural-based NLP, and it definitely outperforms all the historical NLP methodologies that came before it, so that's what we're going to be focusing on. But NLP is basically a field which is the intersection between computers and natural language, basically trying to get computers to process and analyze natural language. And it's a very umbrella field, and it covers a lot of topics such as translation, natural language generation, entity detection, sentiment classification, and many other things. There's a diagram which I have just here, which will you know, show us the power of what NLP can actually do. And research into the NLP started quite early on, in the 50s, and obviously today's systems are, you know, masses and masses better than what there was 70 years ago, but NLP is still considered an unsolved problem, and research is evolving at such a rapid pace within it. One of the reasons why it is considered unsolved, or not why it's considered unsolved, but why it's challenging to solve it, is because of the ambiguity of language. For example, the word mean has many different definitions. So one could be average, like the mean of 5 numbers. The other one could mean signify, forgive the pun, there'll be a lot of them over the course of the workshop. And the other one, like mean as in unkind. We also find ourselves using idioms a lot in language, and that's phrases for which the meaning doesn't represent the sequence of words directly. So, she was over the moon doesn't literally mean that, you know, she jumped over the moon or something. Specifically looking at translation, word order also proves to be a problem. And the example I give here is going from German to English. So if you were to translate this sentence word by word, you would get yesterday I have to London been, whereas the correct translation is yesterday I have been to London. So we can't, you know, when it comes to translation, we can't take each of these individual words, find what it means in English, and then, you know, compose a sentence off of that. That doesn't really work. NLP can, or the history of NLP can essentially be broken down into three separate phases: the rule-based, the statistical, and the neural. The rule-based focused on, you know, using handcrafted rules to try and model linguistic intuitions, whereas the statistical tries to use they could be parametric models, but maybe you know, non-parametric ways of trying to translate or do whatever. Neural based, what we try to do with neural NLP is we try to learn representations from our data and use those representations of words, for example, to feed into a deep model which can understand the high dimensional space of our representations. And neural approaches in NLP allow us to solve, or generally speaking, allow us to solve the following kinds of problems: one to many, many to one, many to many, and many to many. The one-to-one case is simply a neural network. So let me explain what these boxes are. So every blue here is an input to the network, and the network is represented by either this orange box or this sequence of orange boxes. The output could be many outputs. So for example, a one-to-many would be image classification, right? You have one input and then you run this input through a model and you get a sequence of outputs, right? So I feed in this book and I get a sequence of outputs saying a book titled Computer Networking, for example. Many to one, an example of many to one would be sentiment classification, for example. We go from a sentence or a review of some sort and we say, okay, given this sequence of words, how do we want to, what is the sentiment behind it? Is it positive? Is it negative? Or, what is the ranking of this if we were trying to automatically assign like a star rating to movie reviews or something, which is the example we'll be looking at later on in this lecture. What is the rating that we apply to, what is the star rating that this sequence basically tries to encode? Guys, I'm just going to give you 30 seconds while I read through the new comments, but if you can list examples of many-to-many, these two different kinds of many-to-many, we'll see if you can come up with anything, and doesn't matter if you can, doesn't matter if you can't, we'll run through some examples, but just to make sure you guys are following what I'm saying so far in terms of the diagram. Okay, cool. So one example of many-to-many is, this first example is translation. So we feed in a whole source sentence. Let's say, this sentence in German. Gestern bin ich in London gewesen. Apologies for any German people out there. My German isn't the greatest. We then start, once our network has processed this input sequence, we then start generating an output sequence, which is the translation. So we've processed, this German sentence, and now we want our network to output, yesterday I have been to London. The other example of many-to-many would be video captioning, for example. I think that's the most intuitive out of the two that I've listed there. So we feed in like frames of a video, and we want to caption each frame. So at every frame we feed in, we want to output some caption or some word, for example. The difference between this many-to-many and this many-to-many is that in this many-to-many, we have our whole input being fed in once before we start creating the output. Whereas with this many-to-many, we create the output as we feed in the input. So there's no processing of the whole input sequence, because the whole input sequence might not be available for a given time step. Okay, hope everyone follows that. Again, feel free to drop any comments. If you haven't, I assume that you're understanding this fine. Okay, so how can we get computers to represent our natural language data? What we're going to do is we're going to have this kind of running example, which we're going to run with for the rest of this workshop. We have a list of movie reviews, okay? So this movie had a brilliant storyline with great action. Some parts were not so great, but overall pretty okay. And my dog went to sleep watching this trash movie. So we're going to assume that, some kind of model which can take this input exists, and it will generate some kind of output. The problem that we have so far is, how do we go from this raw text data to feeding it into our model, whether that's a neural network, or a recurrent neural network, or any kind of model that we want to use. How can we go from this natural language data to something which our model can understand? Guys, if you wanna comment on your thoughts and ideas, that'd be cool. Okay, one possible solution is to one-hot our corpus based on our vocabulary. So there are 4 terms that you're going to learn here, and understanding these 4 terms is basically critical to understanding the rest of the lecture. So it's really important that you guys understand these simple terms. So we have a vocabulary, a corpus, a token, and a sequence. And to go from our natural language data to something which our computer can understand, we need to one-hot our corpus based on the tokens, which is what we use to generate our vocabulary. So let's break this down term by term. Okay, so a token is the atomic unit of a sequence, and the example of that is not an example, but I guess it is an example. One example of a token is a word. But another example could be punctuation or an emoji, right? It's just something which the aggregation of which represents the sequence as a whole. So in this sequence that we have, which can be thought of as analogously to a sentence, but a sequence is just a sequence of words. The reason we make that distinction between sequence and sentence is because we might have phrases, and phrases aren't technically sentences, but they are a sequence of words. So a sequence is just kind of the abstract term that we use there. So the sequence, this movie had a brilliant storyline with great action, is composed of 10 tokens, right? Because we have 10 words. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Our corpus is basically our input data. And in this example here, it is the collection of these sequences. So our corpus is this sequence, and this sequence. When we look at language modeling and more complicated examples, we might be using the whole of Wikipedia as our corpus. This is just the natural language term that we assign to our input data. Our vocabulary is the set of unique tokens in our corpus, right? So here we have, just a vocabulary which is 10,000 words long, and this vocabulary represents the unique words that we have in our corpus. Not specifically this corpus, this is just an example, but a vocabulary is the list of unique tokens in our corpus. So here we see like this toy vocabulary has a vocabulary size of 10,000, and what this means is that there's 10,000 unique tokens in our vocabulary. Now what we said is we're going to one-hot our corpus based on our vocabulary. What does this mean? So we have a sequence, and we have indexes which map these individual tokens to a number. Okay, so what we're going to do is, for one sequence, we're going to have the sequence length is 10, right? As I said earlier on, we have 10 tokens in this sequence, and to one-hot it, each one of these sequences, each one of the words in the sequence needs to be represented by a vector, where it's zeros everywhere and a 1 where we have the relevant index in the vocabulary. So looking through the sequence, we see the first word this, and we see in our vocabulary, this occurs at index 7,431. And our total vocabulary length is 10,000. So we're going to have a vector, which is of sequence length, which is of, for one word, which is of vocabulary size. So for the word this, we will have a vector which is 10,000 long because our vocabulary size is 10,000, but at index 7,431, it'll be 1. Everywhere else, it will be zeros. And we need to do this for every sequence in our corpus. So I understand it's a bit small. If you have the Jupyter Notebook up, maybe you can see it a bit more clearly. But our one-hot matrix, which is all the one-hot vectors for our sequence, will be of size sequence length times vocab size. And what this means is, I'll dive a bit more into this into the next image. But what this means is, we will have, because the sequence length is 10, we will have 10 entries of those 10,000 long vectors. So one entry is for one word. Our first entry for the word this, as I mentioned, has a 1 at index 7,431. Our second entry, movie, has a 1 at index 4,800, and so forth. So A might be, index 25 or something, and that will be the fourth entry in our one-hot matrix. Okay, feel free to ask questions, guys. I'll check back now every now and then to see if there is anything that you guys need help with. Okay, so let's actually build this, this one-hot matrix that I was talking about. So we have our corpus, which we've just loaded in as a list of lists, we've removed the emoji for now, and we'll have a brief discussion on that later about what we can do with, these bit more ambiguous symbols. So we're going to tokenize our corpus, and what this means is that we're going to split the corpus from the sentence level, so the sentence level, to the word level. So instead of having, I guess we'll run this code and we'll see what it looks like. So instead of having, for one of the lists, instead of having a string, which is the whole sentence, we've now got a string for each individual token. So we now have a list of tokens for one sequence instead of one string for one sequence. So we can see that we still have the same list of lists, right? We still have a list of lists, and each list in this list of lists in our now tokenized corpus is each token as an individual element in the list. So we've now tokenized this corpus. And now what we're going to do, we're going to load in a vocabulary. So in this particular case, and this isn't normally what you do in practice, but just as an introduction, we're going to load in an external file for our vocabulary. And this is just the top 10,000 most common words in the English language. And as I mentioned, a vocabulary is simply a list of unique words which we can perform lookups against. Later on, we'll look at how we can use our own corpus to generate our vocabulary. But for now, we're just going to be looking at a preloaded vocabulary. So we're going to load in our vocabulary file, and then we're going to basically say, okay, let's just have each individual word as an element in a list. And now we're going to print the 5 most common words in the English language, which is the, of, and, to, and a. Sorry, what do you mean, how come you can't use the index? Could you just clarify a bit? I'm not 100% sure what you mean by that. Okay, guys, it's really important to kind of understand the conception behind this image. And the important part is these numbers here, 3, 10, and 10,000. This is what we refer to as a shape of a tensor. So typically when we're doing deep learning, and in this particular case NLP, we have something which is batch size times features. Because we're working with sequences of data, we add another dimension to the tensor. We have something which is batch size, sequence length, feature size. In our example, we have 3 different sentences, right? And we can only feed in a sequence at a time, or we want one matrix. So for example, this matrix to encode one sequence, right? And we have 3 sequences. So what this means is that we'll have a batch size of 3 because there are 3 sequences. Each of the sequences are 10 long, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the one without the emoji. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each of these is going to be represented by a vector. Each one of those 10 elements in our matrix is going to be represented by a 10,000 long vector, right? That means this vector has 10,000 dimensions. Oh, do you mean like using the number 1, using the number 2, using the number 3 to represent each of the individual words, as opposed to one hot encoding? Okay, so the reason for that is if you recall kind of the operations that a neural network does, is it multiplies some weights by... Actually, I might have a question on this later. Okay, no. It multiplies some weights by a numeric value. What we've done, if we do that, is we've now basically said that this particular word multiplies this weight by... this particular word now scales the elements of our neural network disproportionately to all the other words because it's just a higher number. So we need some way to when we feed in our sequence to the network, so the network knows that, oh, we can't treat this word as more influential than another word just based on the original numeric encoding of that word. Please let me know if that doesn't answer your question, and obviously I'll cover it when we as we progress down the lecture. Okay, so let's actually build this one hot tensor. So we're gonna use NumPy for now before starting with PyTorch, and we're gonna define our getOneHotCorpus function. This is going to take in our corpus, which is going to be a list of lists, our tokenized corpus, which is going to be this again list of lists, but instead of each list being the string of the sequence, we're going to have each list be the tokens within the sequence. So this output here. And our vocabulary, which is going to be this 10,000 word file that we've loaded in. So first of all, we're going to define our corpus size to be the length of the corpus, and we're going to define the max length of our sequence, which is the highest, or the sequence which has the most words in it is going to be the max length, is going to be equal to the max length sequence. And I'll talk about why that is in a second. And our vocab length, which is the length of the vocabulary. So here we see that corpus size is the length of the corpus, so we can expect it to be 3, right? Because we have 3 entries in our corpus. The max length of the sequence is going to be the sequence is going to be equal to the number of tokens in our longest sequence. In our example, they were all 10, but this isn't a very realistic example. We can expect some movie reviews to be, 3 words, 4 words long, and some to be hundreds of words long. And the reason that we take the max length is because we want to... We need all of our inputs to be the same shape when we feed them into the network. So if we have, let's say our max, the longest sequence that we have in our corpus is 20 words, and the shortest is 5 words. That means we have a 15-word discrepancy between the longest sequence and the shortest sequence. And what we're going to do is simply, if we're looking at a sequence which isn't the longest sequence, we're just going to add vectors of zeros. So like a zero hot vector, right? There's not a 1 anywhere, and this is just going to be padding. So this is just going to be, okay, after these 5 words, we've hit the end of the sequence, but for implementation reasons only, we need to have padding there to make sure all of our tensors or all of our sequence matrices are of the same length. And our vocab length is essentially going to be the length of the vector, because this is what we compute the 1 hot encoding against. Okay, guys, so this is some code for you to do. I want you guys to take 5 minutes to finish off this function and run this function. You should see an error with this function. That's expected. And think about answering this question: how can you get around this? How can you get around this this limitation that a 1 hot or a fixed size vocabulary provides? So we'll take 5 minutes. Come back at 36 past, 37 past, and feel free to ask questions. I'll still be here looking over the chat. And yeah, see you in a bit, guys. All right, guys, welcome back. Guys, you should check out our group feature that we've just implemented. Got live. I think this is the first session it's actually live for. During our code breaks, you can quickly hop in there, and me, Harry, and everybody else who's viewing as well will be around in that group, and then you can share your screen, talk to each other, and try and solve the tasks together. It's really cool. Check it out. Let's check it out now. See what's okay. I'm the only one in my group, but
Yeah.
thanks, bro. All right, let's continue. So what we're going to do first of all is we're going to create a three-dimensional array, or otherwise known as a tensor, rank 3, and we're going to initialize it to zeros. So this will be tokenized corpus. Okay, so one hot array equals mp.zeros, and the shape is going to be 3 times 10 times 10,000, or we should really be doing it using variables. So corpus size, let's see this, corpus size, max len sequence, vocab len. Now we need to find, okay, now we're going to loop over our tokenized corpus. So we have the index of the corpus that we're currently looping over. So, and the actual tokenized sentence itself, right? And for every sequence index and the token in the token for in the tokenized sentence, we want to find the index of that token. So to do that, we will need to have a lookup against our vocabulary. So token index equals vocabulary dot index token, and for the relevant value in the NumPy array, we need to change the relevant value to 1. Sorry, it should say 1, not zeros. For the relevant value in our NumPy array, we need to change it to 1. So we have this three-dimensional array of zeros, which is currently 3, 10, 10,000. And now we need to say, okay, so our one hot array at corpus index sequence index token index equals 1. I think that's right. Let's check. Yeah. Okay. So let's just talk about the for loop, just so you guys are a bit clearer on that. So for every sentence in our tokenized corpus, or for every tokenized sentence in our tokenized corpus, which is every one of these, so first iteration, second iteration, third iteration, we're gonna look at each of the individual tokens in that tokenized sentence, and we also have the sequence index of that. So for this corpus, for this sentence or sequence, this is obviously 0, 1, 2, 3, blah blah blah, and we're gonna change the value in our one hot array to the corpus index which we're currently considering, for the sequence index that we're currently considering, for the token that we've looked up. So, and we're going to change that from a 0 to a 1. And we're going to print that, and the shape should be 3 times 10 times 10,000. Name one hot corpus is not defined. Okay, sorry, this should be called one hot corpus. One hot corpus. Okay, let's see what happens when we actually print our one hot corpus. Okay, we only see a 1 here because obviously it's too long to print 10,000, but the fact that I see a 1 here does indicate that this has worked. Okay, so let's try and add some new reviews to our corpus. So we got 2 new reviews. Good movie, and this movie had a significant amount of flaws. We're gonna extend our corpus with these new reviews, and now we're gonna try and one hot our corpus again. Okay. So we see that the word flaws is not in this vocabulary file that we loaded in. Now, one possible solution is, okay, we can just have a bigger vocabulary. But the problem with this is that 10,000 dimensions is already a ridiculous amount to represent for one token. And by just adding more and more words in, we're just going to be having higher and higher dimensions. And this is going to be, as the number of dimensions increase, more and more computationally infeasible. So that's one aspect of why one-hot encoding is bad. The other aspect is that there's no notion of similarity between words. So dog and hound, even though these 2 words are synonyms of each other, if you one-hot them, you have a 1, in the location of the word dog, and a 1 in the location of the word hound. Now, when you compare those 2, there's no difference between the distance, if you're in one-hot vector terms, between dog and hound and dog and potato, for example. Even though dog should be, dog is a lot more similar to hound than it is to potato, there's no notion of similarity which can be encoded in this in a one-hot vector. Cool. Yeah. Okay. So what we're now going to try and look at is something called distributed representations. And to provide a high-level intuition behind what this term means is that we're going to represent our words as vectors. We're going to have some kind of dense encoding scheme that we use to try and have each one of our tokens represented as as something which we can compute similarity between 2 things against. This is heavily inspired by a quote from Firth, who was a linguist, and as you can see, it came quite early on, about 60 to 70 years ago, saying, "You shall know a word by the company it keeps." And his hypothesis or his theory was basically that every word is defined by the words that surround that word. So I guess there's no good examples in this sentence, but we will see some later on. But basically the meaning of a word is defined by the context that word appears in over many contexts. And before we focus on actually how to do this with words themselves, let's try and build an intuition behind how it works and why it works. And we're going to do this by looking at, first of all, 2-dimensional representations. And then we'll scale this up to 3-dimensional representations to show how the concepts in 2 dimensions can be extended to 3 dimensions. And then to n dimensions. So basically any other dimension. And what we're going to do is we're going to look at animal cuteness versus animal size. So I've just created this table here. These are all done out of my own opinion. So sorry if you disagree. Okay, so just coding up the stats of this table, and we're using a graphing library called Plotly to plot the animal cuteness versus animal size. Let's fill it in. Okay. So this is basically a visual representation of this table here. And as you can see, this visual representation kind of allows us to think of things in... it kind of allows us to have a notion of distance, and allows us to think of these things differently than we would be able to just by looking at this table. So we can see here that the closest animal to alligator is hyena. And what we can actually do is work out the distance between alligator and hyena. And if you think back to secondary school maths, this is simply just the Euclidean distance or Pythagoras' theorem. So we'll just code up our function, which given any two coordinates of two different animals, we'll return the distance between them. So this is x1 minus x2 squared plus y1 minus minus y2 squared, all square rooted. This is just a simple helper function to, given an animal name, it will return, its stats, so its cuteness and size. So given alligator, for example, it will return 840, and given hyena, it will return 1030. And then we're gonna plug in our cuteness and size for an alligator and for a hyena, and we're going to work out the distance, and we're going to compare that to an alligator and an elephant. So we can see here that the distance between an alligator and a hyena is a lot lower than an alligator and an elephant. And visually we can see this as well, right? Like alligator and hyena are right next to each other compared to alligator and elephant, which are quite far away from each other. So alligator is more similar to hyena than it is to elephant. This kind of visual representation allows us to reason about lots of different things. We can now ask, for example, what's halfway between a wasp and a horse? And this isn't something that we can easily understand by just looking at this table of numbers, right? There's kind of this visual representation which allows us to form these kinds of analogies. So we can say, okay, what's halfway between a wasp and a horse? Oh, look, if we drew a line about halfway through, it'd be a pig. And we can actually we can actually code this up. So we'll do that in a second. The other thing I have mentioned here is that we can do analogies as well. We can say pig is to horse as mouse is to what. So, we can say, okay, pig is similar to horse as mouse is to, obviously, in this case, lion. But we can kind of see this information, and we can kind of do this analogical reasoning as well, just by using these data points. So okay, so we're actually going to code this up, how to do this analogy. So we get the horse cuteness and the horse size and the pig cuteness and the pig size, and we'll just plot them. We'll plot a line between the midpoints of the two. Now, essentially what we want to do is, it's not a translation, but we want to move this line onto mouse and see where the end ends up, right? And the point the animal which ends up closest to this point is the answer to this analogy. Pig is to horse as mouse is to what? So guys, I just want you to attempt this out. This is maybe another 5 minutes. Yeah, just another 5 minutes just to code this up, see if you can come up with cool ideas, see if you can try and get a plot going for something which is halfway between a mosquito and a horse as well, if you finish this relatively quickly. We'll be back at probably 55 past.
Meet us in the lobbies. So meet us in the lobbies.
Yeah, come through to the lobbies, because I'll be there if you wanna ask me questions or something.
Tell them allow their group camera, and go to the group section.
Yeah. So click on the group thing here, and if you haven't already, you know, allow your camera access, and we should be able to see you.
Might just be me and you, chat.
Could be. What the fuck? Oh, there we go. Okay, one sec.
Hey guys, I don't see anything.
I see you.
You see me?
Yeah. My camera's off though. Let me.
Chat gone for you as well.
I see. Hey guys, I don't see anything, but. Oh, it says when I try to click join that I'm already.
As well, you've seen me here, obviously. Neo just.
Yo.
His head shape. Yeah. Wow, it's a good time too. He's the expert. Yeah, no, he had super long hair before as well. Yeah. No, but I got a nice little fade, which Harun did for me. Yeah.
Okay. Cool.
So, yeah, it seems to be going alright.
It's a bit distracting, bro.
Sorry, is
Yeah,
that?
you're talking. Yeah.
I should move somewhere else.
Yeah.
So everyone else can hear me.
Okay. So we're gonna plot
I'm
our.
gonna go back to class on the next session.
Yeah. So we're gonna plot our new figure, which will show this line essentially translated from move to mouse as well. So here we had, if I just copy this line so we can use it as reference. Here we had our X as pig cuteness and horse cuteness. And now what we want to do is have our X as mouse cuteness, because that's where we're starting from. And we want to move this to mouse cuteness plus the difference. So we will plus pig horse diff cuteness. And similar thing for our Y. So we start at mouse cuteness and we move that up to pig horse diff size. Cutness is not defined, and this isn't meant to be cutness anyway, it's meant to be mouse size. And we're not cutting mice here, we're just seeing how cute they are. Okay, as we can see, the closest animal to this point here is a lion. Now, this concept of distance and analogical, don't know what the word is, analogical reasoning, can also be extended to higher dimensions. So again, before we focus on words, let's just add another dimension to our dataset and see what it looks like. So here we're now adding the ferocity of the animal as well. And we'll just add another, another list to which represents ferocity, and we'll plot that on a 3D plot. In a second, the 3D plots take a sec to render. Cool. Okay, so it's a bit harder to gain the same intuition in the 3D example as a 2D example, but we can still see that, you know, alligator and hyena are very close together in our 3D space. Let's try and get a good angle on that. And, you know, alligator and elephant are still quite far apart. So we're just going to redefine our get animal info function to return the animal ferocity as well for a given animal name. And now we need to work out the distance between vectors in 3D space. So we have our generalized distance formula for n dimensions, right? And this is what n refers to. N is the number of dimensions that we have. So this is simply this is the Euclidean distance. So the sum over all of our the difference between the two vectors squared and the square root of all of that. And we have an example here on the side. So we have two vectors which we want to work out a distance between. In this case, you know, the two vectors we're going to be considering are going to be two animal vectors, and the elements in those vectors are going to be the cuteness, the size, and the ferocity, right? So if we were comparing, if we wanted to work out the distance between lion and elephant, for example, our vectors would be 80, 50, 85, and 75, 95, and 20. Then we're going to take each of the individual elements, which is the I here. So this is a loop for every element in, you know, or in our n dimensions. Take the ith element from the first, subtract it from the ith element in the second vector, square that, sum it over all the elements in the vector, and then take the square root. So here we can see 1 minus 2 squared, 5 minus 3 squared, 3 minus 7 squared, 2 minus 3 squared, all square rooted, and we get the answer of root 22. Guys, if you could... sorry, this should say vector, not coord, just to keep the terminology the same. If you guys could just try and code up this formula in here, we'll give you... see what else if you can... Yeah, if you just take 5 minutes to code up this function, and we'll be in the groups. We'll come and assist you if you need help. Okay, guys, sorry about that. We're back. So just coding up the answer to this function. So you can do this in like a for loop or something. I found this pretty cool one-liner. I coded this pretty cool one-liner. What we're gonna do, we're gonna zip vector 1 and 2. So basically, what this means is every time we loop over it, we will take this is loop 1. This is loop 2, this is loop 3, and this is loop 4, for example. So that's I and j. And then we're going to square I and j. And this is going to be a list. So this is a list comprehension. And then we're going to sum all of it, which is this sigma here. And then we are going to take the square root of all of that. And that's going to give us our distance. So let's plot the distance between a hyena and an alligator, and a hyena and a dog. So we can see that the distance between a hyena and an alligator is relatively unchanged from what it was in the 2D example, because their ferocity is the same, and they're right next to each other. But the distance between a hyena and the dog is obviously a lot larger. So you can see, like, you know, basically whatever angle you look at it from, the dog is constantly far away from hyena. Now we have this notion of, we had it in the 2D example as well, but we have this notion of closest to, right? So given any certain animal, what is the closest, what are the closest animals to that particular animal? So, you know, looking at this visually, the closest, you know, 3 animals to a hyena would probably be an alligator, a wasp, and either a mole or maybe a giraffe, one of the two. I'm not 100% sure, but we can find that out. So to do this, we're going to loop over every animal that we have in our animal list, which is animal info. So animal info is all of the animals along with their cuteness, their size, and their ferocity. We're going to have this closest to function, which takes in as input the name of the animal we want to find the closest thing to. Sorry guys, I'll just stop this noise. So we're passing in as an argument the name of the animal we want to find the other animals which it is closest to. And we'll just extract the statistics for that animal using the helper function we defined previously. And we'll initialize a list of the distances of the other animals from the animal we want to find the distances for. Okay, so for every animal in our animal info, you know, if that animal is the animal we want to find the stats for, we'll just skip that loop. And then what we'll do is we'll find the distance between the animal that we want, so primary animal stats, and the secondary animal stat, which is the looping over all the animals. And this is just a tuple, so, you know, we're just going to say, okay, the distance between hyena and dog, for example, is the first element in this tuple is going to be dog, and then we're going to have the distance there. And then we're just going to sort the list in order and return the sorted list up to the n elements that we want. So the closest 3 animals, for example, in this case. So closest to horse is giraffe, elephant, and pig. The example that I was talking about was hyena, so let's see. So alligator, wasp, and lion are the closest 3. Okay, so alligator obviously makes sense, wasp makes sense, and lion and giraffe are pretty close to each other, but the math is telling us that lion is closer to alligator than giraffe. Okay, it's actually possible to do similar kind of reasoning with words. I'm going to look at the methodology of obtaining those word vectors later on. But before I do that, I want to talk about why representing words as vectors is effective. And actually, one of the reasons is not related to anything that I've mentioned before, but it's because they can be pre-trained. And what this means is that we can use word vectors which have been trained on any given corpus: Wikipedia, Twitter, medical journal, ancient religious texts, this computer networking book, whatever. And we can use these vectors in a potentially domain-specific downstream task. So word vectors which we've obtained by training on ancient religious texts might be used to classify different ancient religious texts, or even the same ancient religious texts, into a religion. Or Twitter data could be used to generate conversation-like agents, because it's a very informal language that's going on there. So each word vector is just a vector to represent that word, and the algorithm we're using to solve the task, whether it's the classification of ancient religions or the generation of conversation-like agents, will learn the embeddings of the word based on their context in the training corpus. So these models don't have access to natural language as we know it. They only have access to natural language within the corpus you're training them in. Corpus, by all means, could be the combination of Wikipedia and all of Twitter, for example. But just to keep it a bit finer-grained when I'm discussing these concepts, the embeddings of the words are based on the context that they appear in the training corpus. So the meaning of the word lit would be different if it was trained, if the corpus that the word embedding model was trained on was a religious text versus if it was trained on Twitter. So if it was trained in a religious text, it would mean like, oh, he lit a fire or something. It would tend to correspond very highly to light. Whereas with Twitter, we're probably talking about it's absolutely fantastic. So again, before going into how we obtain these and actually pre-training these embeddings, we're gonna look and analyze some word vectors. So here we looked at concepts in 3 dimensions, but this notion of a distance and similarity and analogical reasoning can actually apply to higher dimensions as well. And what we're loading in here is a file which is 50 dimensions long, trained with a word embedding algorithm called glove. This is just a truncated file because the whole file is too big, and for our purposes this will serve fine. So we're just loading it in, and we're just going to create a dictionary where the key is the word and the value is the word vector. So this is the vector for the word the. Did you have horse as the example that you were doing it closest to for the person who said they got giraffe, lion, and elephant? Yeah, I changed it. I changed this closest to hyena because I was just talking about hyena. If I do a horse, then I expect it to be giraffe, elephant, and pig. Interestingly. Okay, cool. Okay, yeah, so this is the vector for the word the, and it is not meant to be understandable by humans whatsoever, okay? This is meant to be only for computers to actually understand, what's going on. Like, there's no way that somebody can read this and be like, oh yeah, that probably refers to the word the. Okay, I'm going to load in the vectors for king, queen, man, woman, water, and earth. And we're going to visualize what they actually look like. So in this diagram, red represents lower values, white is probably representing something around 0, and blue represents higher values. So these values are typically constrained within the -1 to 1 range, but that might not always be the case. But we can see here that, we can find, we see this very nice visual similarity between you know, king and queen and man and woman, and how much it differs from something like water and earth. So earth is kind of an abstract term. Water is kind of like a very physical term, which, you know, these reds might be showing some sort of indication towards. Whereas, you know, these terms represent some, you know, so we know what they represent, but we're looking here to see how the computer knows what they represent. So let's look and see if we see anything which is common between king and queen, but not in man and woman. Okay, so this here, dimension 15, we see that these vectors are quite similar to each other. So maybe this vector is some form of encoding of royalty. So if we were to plot prince or princess or baron or dame or something, then you know, only looking at these two examples, I would expect this this 15th dimension to be of a similar color. Similarly, there might be some kind of correlation between queen and woman, and I think 16 might be some kind of encoding of that. Also 5 looks like we have similar things in 5 which we don't have in man and for man and king. Okay, so as I mentioned already, we can apply analogies to word vectors, and obviously these analogies take place in by using the concept of distance. Now, in high dimensional space, the kind of norm is to use cosine distance instead of Euclidean distance, but the reason for this isn't entirely strong. Well, you know, when I was looking up the reason why, there wasn't really like a strong indication of why you should be using one over the other. I think it is just the norm to use cosine distance, but with whatever data set that you work with, you should be experimenting with both cosine and Euclidean to see which one is preferable, or which one results in better things for your data set. Okay, so just thinking back to 2D space, for example, the Euclidean distance measures the magnitude between the two points, right? So, yeah, the magnitude is just the distance formula which was given above, the square roots of the difference in length between the 2 points versus the difference in height. Now, we can always also use the angle between 2 points as a way of capturing similarity or distance. And the similarity can be expressed, so here for P1 and P2, we can say that P1 is distance D apart from P2, where D is the theta angle distance. And this similarity can be expressed as a function over theta, and it's called the cosine distance because it is cos theta, which will give you, which will move this P2 to give the answer to how similar P1 and P2 are. So actually, the cosine distance is just the dot product over the norms of the vector, right? So if all the vectors were normalized, which is given by this formula here, so it's just the square, the summation of the square of every individual element in that vector square rooted, then this is just this bottom denominator is 1. So under the assumption that the vectors are normalized, the cosine similarity is essentially just the dot product. And this is a brilliant way to actually think about what the dot product is doing, right? Anytime you see the dot product in terms of matrix, in you know, vector or matrix maths, all you need to do is just think about it. Okay, we're trying to compute the similarity between this variable and this variable, and that's what the dot product is doing. How similar are these two variables together? So before actually finding or applying any of the analogies that we're going to do, we need to define a function which finds the closest vector to another vector. Guys, I'm going to give you another 5 minutes. I want you to read through this code, understand what it's doing. Obviously, I'll run through it when we're back, but if you can build up an understanding of it, that's cool. And also try and answer these questions using using the kind of analogies in the same way that we've done the analogies above. Here's an example, but don't tell anyone about that. Okay, I see a question. I'm just gonna answer it. Have you considered using both Euclidean and cosine distances? I think they can be used and helpful to see more about word embeddings. Yeah, honestly, it depends on the... I don't want to say depends because I don't think that's the right word to use, but different use cases will find that sometimes Euclidean distance works better to optimize whatever metric they want to optimize, and sometimes cosine distance works better to optimize whatever metric they want to optimize. So it is very much on a case by case basis, and there are definitely other distance algorithms which exist. And because it's on a case by case basis, there isn't really much point for me to cover to cover all those different distance algorithms. The reason I wanted to talk about cosine distance in particular today was because of its relation to the dot product and it being a very intuitive way to think about what the dot product is actually doing. Great question though. Obviously, guys, if you have any more, feel free to throw them in and ask them. Apologies, guys. My sound was off. Okay, let me start again. So I'm just going to run through this function before talking about how to actually before actually coding the analogies up. So we're going to import cosine from SciPy, and we're going to define this function, which takes in the vector we want to find the closest other vector to, and an exclude list, which basically says, okay, don't consider these vectors, just skip over these vectors. And when we get to coding up the analogy, I'll talk a bit more about that. So we're going to initialize the closest distance and the closest token. And for every token and vector that we have in our glove vectors dictionary, which we defined earlier on, we're going to work out the distance, the cosine distance between the argument that we pass in and the vector which we're currently looping over. Now, if the closest distance is greater than the distance, and the token is not in the exclude list, which we defined here, our new distance is, or our new closest distance is the distance, and our new closest token is that token. Okay, so let's find out the answer to king minus man plus woman. Okay, so we have our king vector minus man vector plus woman vector. Okay, to find closest. Okay, so literally king minus man plus woman. I'm going to pass this into our find closest function to find closest. And what we're going to use this exclude list to say, okay, do not consider the token king, man, or woman. And voila, we get queen. And this kind of makes sense, doesn't it? That king, take away a man, and add a woman is actually a queen. I think that's fucking cool. And we can do the same with this more kind of analogical reasoning. So we have to find closest equals vector of London minus England plus Paris. Okay, and then find closest and we're not going to consider London, England, or Paris. Glove vector is not defined. Okay. Moscow, interesting. Okay. Maybe it's because we need to do England minus London. France. Okay. So this actually brings me to a good point, which is that this kind of like addition and algebra that we're doing over using these word embeddings, it's one, not an exact science, and this is partially because of biases in the training data, and the fact that, you know, this is actually, you know, even though it's objectively new, you know, like 2013 or 2012 to 2013 or something, can't remember off the top of my head. What was I saying? Even though it's objectively, in terms of modern NLP, it's not really, it's nowhere near the state of the art whatsoever. This is something that we're looking at more with pre-trained language models in our last lecture. But this just kind of gives you like, okay, if we were to represent words as vectors, this is kind of the thing that we want to do. And as a first step towards having these kinds of distributed representations or dense representations of words as vectors, I think it's really impressive that we can perform this kind of reasoning on them. And obviously, as systems get better, these kinds of reasonings get better as well. So the cool thing about this is that we can actually also semantically reason as opposed to just using it for analogies. And what I mean by this is we can say, okay, well, France plus capital is what? Well, obviously we know it's Paris, but this kind of adding this term of capital to France kind of pushes the meaning of what we want to find to be more. I don't even know what I'm saying here, but you can kind of understand how having this entity and having this concept and adding the two together is viable with word vectors. And out of curiosity, I'm kind of curious what happens if we put in Paris minus capital. Do we get France? Well, I imagine we would, right? Jean. Interesting. So yeah, as I said, this isn't really an exact science. I'm not sure why Jean has been returned from that. But the key takeaway of this is that distributed vectors group similar words and objects together. And as we can see from this, like king and queen are grouped more closely than king and water or king and earth, for example, because they appear in similar contexts in our corpus. Yeah, sorry, I'll zoom in. And what was this other question? The Euclidean in find closest function. Oh, the exclude list. The exclude list is just there to say these are the vectors that we want to find the closest label to this king vector, man vector, and woman vector, for example. But if the vector that it is closest to this vector is either king, man, or woman, just this isn't the answer we want. We want an answer which isn't in the question we're asking. I think this kind of it's a kind of a hack for this word for this glove algorithm and the Word2Vec algorithm we'll be looking at today. But with more modern day systems, I think this exclude list probably isn't necessary, and it can understand that implicitly know that okay, we don't want to. It will have more precise vectors for each of the for every token that we have in our corpus. Okay, guys, we're going to take a... let me see when we have the next code break. Okay, I'm going to run through this section, and then we'll take a bit of a break. Okay, so we've just looked at what distributed vectors actually are and the kinds of things that we can do with representing words as vectors. Now what we want to do is, going back to our original problem, we need to get this text into a format where we can actually put those texts where we can actually map those tokens to a vector. And this part of the NLP pipeline is called preprocessing. I might have zoomed in a bit too much there. Okay, so we kind of need to clean our data set, and what we're going to do is, along with those 3 reviews that we had earlier on, we're going to add some more movie reviews. So this is just going to change our corpus that we defined earlier on into something more that you'd find like in production. So instead of a list of lists, it's just going to originally be a list of strings, as is here. and then we're just gonna extend the corpus that we had to these more movie reviews. So our new movie review list contains those 3 that we had earlier on, and a bunch more with different types of noise in there, which I'll be covering in a second. Okay, so we want to tokenize this corpus, and how we're gonna tokenize it right now is just splitting on white space. So okay, we're gonna say return. No. Okay, so for sequence in corpus. Tokenized corpus is going to be initialized as an empty list. And we're going to append the sequence which has been split on white spaces. Print that, we should get a tokenized. We should get a list of lists, which we don't because we didn't return this. Again, still none. Corpus. Alright, let's try debug this. Okay, and then we want to turn tokenized. Oh, okay. No, whoops. Sorry. New error, guys. New error. Actually, I'll just get rid of this line. Uncomment this. Get rid of the return and return that. Okay, there we go. So we have a list of lists where every sublist is the tokenized sequence that we have for every element in our corpus. Okay, so there are some issues with this, and what these issues are is how's the best way to explain this when it's not live? Okay, first of all, let's just I'll talk about the issues in a second. Let's just list all the tokens that we can see. And we can see we actually have quite a few amount of tokens. Now I've picked out the ones here which cause an issue, or which may potentially be an issue, and I'm gonna print those for our visualization. Okay, so we have movie, film, good, these two, Polish, or is that capital P for Polish and Polish, wildlife, and US. So I think obviously the difference between these 3 are the capitalizations that take place. And what this means is that if we keep it as is, when we feed, when we one-hot our corpus, which we will have to do in a second, and I'll explain why. But when we one-hot our corpus before we feed it into our model, which is going to generate the word embeddings for us, these different spellings of movies will be represented as different. They're not even different spellings. These different capitalizations of movies will be represented as different tokens in our vocabulary, and this isn't something we want, because here movie just refers to movie, right? So we want to essentially normalize this. We want to normalize all of our corpus so it's all in the same format. Film, all of these examples in this list, all of these will be different tokens, right? So different tokens in our vocabulary. So these will be 3 different tokens to represent the word movie, 2 different tokens to represent the word film, 2 different tokens to represent the word good, blah, blah, blah. 3 different tokens to represent the word US or us. Here we want to strip the punctuation away, right? We can say that these 3 ellipses are essentially one token, because it is an atomic unit of a sequence. But, the word film here refers to the same thing. It's referring to a film. But, we got to be careful about the way we do it, because if we just say, okay, let's remove all punctuation, right? Let's just remove, these 3 dots, remove this dot, then we can see some issues coming up with, like, the US acronym. But we can solve this particular example of the US acronym by using a language model, which is what we'll do with Spacey later on in this lecture. But just to keep things simple now, what we're going to do is we're going to normalize our corpus, and we're going to normalize it using regex to lowercase everything and to remove all punctuation. So I'm really not going to dive too much into the details of regex, because those of you who know, it's kind of like a whole lecture in itself. But essentially what we're doing is we're going to, here we split on spaces, right? But now we're going to say, okay, let's split on more than just spaces. Let's split on spaces, which is this dash s, commas, a slash, a full stop, a question mark, a hyphen. This slash here is actually an escape character, so I know it can get kind of confusing. And an apostrophe. So for every review in our corpus, we're going to have the tokenized review, and this tokenized review is going to be split using this this punctuation string that we just defined. Then we're going to just remove all the empty strings from the list and lowercase everything and return that. So we can see here that now, like, I isn't capital. We had a brilliant here, capital brilliant movie there. Let's see in our lowercase list, movie brilliant. Cool. So it looks like everything is kind of normalized. Some things to point out is this method of normalization creates 2 different tokens for words which are split by apostrophes. So the part before the apostrophe and the part after the apostrophe. And now we're going to count just the number of unique tokens we have. Why are we doing that? Oh, just to show that the same issues, or what we had here, has now been mitigated to something which is a bit more normal. So here we had 11 plus 1 plus 1. So 13 times the word movie has appeared, but they appeared in different as different capitalizations. Whereas here, they all appear as movie. And same with film, good, Polish, wildlife. And with US, as I mentioned about the apostrophes here, the same thing happens with full stops. So somewhere in here, I think here. So U and S is split into two different tokens. One for U and one for S, because we split on full stops. Okay. Guys, we're gonna take we'll take a break until 5 to 6. I want you to think about what we need to do with emojis in the meantime. There's really no coding that needs to be done, so it's just a quick break, and we'll be back in a bit. All right. Apologies about that. My bad. Sorry. It's going to be an issue. So what was I saying? Yeah, we can definitely do the tokenization in one line, and I'm sure in my solutions file, if I take a look through it, it's probably there in one line as well. Yeah, just kind of doing it on the spot, I guess. So I did it in 2 lines. Thank you for the comment, though. By normalizing, I always ask, what do we do with the loss of information, and is there a big difference between a halfway solution? So language models tend to solve a lot of the issues that you'd have with that kind of loss of information. I think the most prevalent example is the US example. So a language model would recognize that, oh, in this context, US here is being referred to as the country US, so we can keep that as one token, and we don't need to. It's not an us. That is the closest to like the most natural solution I can think of. I'm not entirely sure what you mean by a halfway solution, because I think the normalization process is definitely important. But there are some things which you'd want to keep as capitals. So these are mainly obviously like proper nouns and names. So the name Thomas, you'd want to keep it with a capital T. And entities as well. So like Apple, you'd want to keep that with a capital A. You don't want to, if it's referring to the entity Apple. Now with rule-based stuff, this is quite difficult, but this is why we have why language models for tokenization exist, and there's something that we'll be looking at very briefly later on into the lecture. Great question though. Thank you for asking. Halfway solutions means capitalizing or dropping punctuations even though it's necessary. Do you mean unnecessary? Punctuation is a token. So we can actually have punctuation as a token. And this is something which is occurring more and more in modern NLP. To be perfectly honest, I'm not sure why people used to remove punctuation. In the statistical systems, that made sense to me, but with the neural-based systems, that never made sense to me, because obviously you can just learn the representation for a punctuation, and it is an atomic unit of a sequence. So in this example, I've just shown you how you could remove punctuation, but in a real-world situation, I probably wouldn't advocate to doing so. Okay, this time we are back and the sound is on. Cool. Alright, so now we get to the meat of this lecture, Word2Vec. So remember what I said at the beginning of the dense representations section. You shall know a word by the company it keeps. And we've demonstrated how this quote is manifested by distributed representations. And this section that we're about to cover discusses and implements one way of obtaining those representations. But actually, there are many ways of doing that. So the reason I chose Word2Vec, and I'll go into a bit more detail about that in a second, but the reason I chose Word2Vec is because it provides simple intuitions about neural networks in general, or not simple, but intuitions about neural networks in general, which we can use to generalize over all concepts of deep learning. And alongside this, it was like the OG, the daddy of the word embedding algorithms which came out. This is really where NLP took off because of Word2Vec. So Word2Vec is actually it refers to a family of neural based algorithms. It's not just one, it's actually two families. And one part of this family consists of two different model architectures, continuous bag of words and skipgram, and the other part focuses on two different approaches to dealing with huge vocabularies, which is what we'd be dealing with if we were, to say using Wikipedia as all of our corpus. Hierarchical softmax and negative sampling. Now, today we're only actually going to be focusing on skipgram. The reason for that is the word vectors that we use in downstream tasks will mainly be using pre-trained, or we won't be using and we'll see more of this next week, we'll be training the word vectors from scratch, where the output isn't a reconstruction of some input sequence. So the other algorithms we can use to obtain word vectors are things like GLOVE, fast text, and more recently pre-trained language models. And this is the pre-trained language models or PLMs is something that we'll be looking more at in future sessions. So once again, let's try and recall the problem that we're trying to solve. Representing our sequences in a way that we can feed into a classifier or a classification model. So we loaded in pre-trained embeddings earlier on, where every vector that we had was a representation for a given word. What the missing part of this loop is how do we actually obtain this representation? So back to this quote. You shall know a word by the company it keeps. We have this notion of company, and well, what does it mean? In the Word2Vec algorithm, the company leads to the term that we call a context window. And this is the words which are in the negative C range to the positive C range of the target context word WT. So for one sequence, which is the first sequence in our review list, this movie had a brilliant storyline with great action. We have the context word W1. And the context window, when the window size is 2, will be the two words which precede it and the two words which proceed it. So the two words which come window size before, the window size words which come before, and the window size words which come after. So for the word this, we don't have anything before. So we have movie and had as the context of the word this, and this creates our training pairs. So our input this and our target movie, and I'll talk about why it's our training pairs in a second. But just know that for every context word that we have, so movie or had, then the training pairs are the tuple of that context word and the words in the window size around it. So the training pairs for the word had would be this, movie, brilliant. So the training pair is input had, output this, input had, output movie, input had, output input had, output brilliant. Okay, so the two variants which I discussed from about Word2Vec earlier on, continuous bag of words, otherwise, I like to call it Sibao instead of Sibo, as I'm sure many of the academics would say it's pronounced, and skipgram. And we're going to focus on skipgram because it's been shown to outperform Sibao on larger corpi, on a larger corpus. Not 100% sure of the plural of that word, but the architecture is slightly different to slightly more complicated than Sibao. But if you can do skipgram, you can do Sibao. So as a challenge to yourself, after this lecture, if you want to try and implement Sibao from scratch, feel free to go ahead and do that. So let's just look at what's going on here, right? So we have 3 layers. We have an input layer, a projection layer, and an output layer. The input layer takes in a word, WT, which in this case would be a context word, WT. It will project it to something, and it will try and predict these outputs. So it will try and predict for the word had. If we feed in the word had as WT, we want our output to be this movie, A Brilliant. And the idea is over a bunch of different different sequences, the words which appear in the sequence will gain some meaning which is based around the words which surround that sequence, surround that context word. So how is this projection done, you might ask? And actually, what it is just the hidden layer of a neural network. So I'm gonna tell you that the input and output are gonna be one hot. So we're gonna have WT as a representation to this skipgram model is gonna be input as a one hot vector, and this output, the target that we try to obtain, is also going to be a one hot vector. Corpora, thank you. I've heard that term enough, so I probably need to stick it in my head. No, the tuple represents input output, and the output is the label. But the feature that we're feeding in as input is going to be a one hot vector, and the label or the output is going to be a one hot vector as well. Not exactly a one hot vector, but a probability distribution over our vocabulary size. And I'll dive more into this. Okay, so how are we actually going to code this up? So this is the image that we just see up here. So just to put this into one image. Okay, so we're going to consider WT to be this, and WT plus J, when J is 1, to be movie. So here we see WT, and WT plus J is movie. So we're going to one-hot the word this, and remember how we one-hot it, yeah? We take our vocabulary, and we just find the index of where the word that we're currently looking for appears. So there's a 1 at index T, and this is our input layer of our neural network. Now we have a hidden layer and an output layer. And between the hidden layer and output layer, obviously there are weight matrices. So our input size is going to be a vocab size, which is V. Then we're going to have something which is our hidden layer, which is going to be of E size, embedding dim size. And embedding dim size is simply the number of features we want to use to represent the word. So when we looked at glove, we had 50-dimensional vectors, these. So the embedding size of this vector is 50. The embedding size of, by definition for all of the tokens in our sequence, that it's going to be fixed because we can't vary the hidden size based on our input. So in this image, our embedding dim is 1, 2, 3, 4, 5, 6. And this weight matrix, and our output is also going to be a vocab size because we want to try and predict the target word. So considering the word this, we want to predict the word movie. So wherever movie appears here, that's what we want y hat to be. We want to optimize to get y hat equal to wt plus j for the current j that we're looking at. Just in a bit more detail, and just to run through this diagram a bit more. So we have a 1 where the word this appears, and what this means is in our weight matrix, which is going to be vocab size times embedding dim, we're going to extract out that vector, because this is essentially when it's a 1 hot, which we're multiplying against a vocabulary size. All we're doing is essentially extracting out the vector where it's a 1, and it's which is going to be this vector here. So all of these will be like a vector for aardvark, a vector for and, a vector for zebra or whatever, and this is our vector for this. And this gets placed into the hidden layer, and what we're going to do is we're going to optimize our network to try and predict a context, a word which is in the context, in the window of the context word. So for this very specific case, as I mentioned already, we have y, which is equal to wt plus j, which equals movie, and we want our prediction to be movie. Okay, did we choose 50 as a fixed value? There are many pre-trained vectors which we can download off the internet. Glove comes in 50 dimensions, 100 dimensions, and 300 dimensions. We can train our own algorithm to be 1000 dimensions. Here I just chose 50 dimensions in the above example to keep the diagram nice and neat. And generally speaking, the more dimensions you have, the richer your representation of the word is going to be. It does plateau, and I think they've, at the time that Glove and Word2Vec were published, they found that this plateau occurs at about 300 dimensions. Now we're working more with dimensions in 500 and 1000, but we're as in with modern NLP, but we're using different methodologies to obtain those embeddings. So with those higher dimensions, those features are still rich, and we're not losing information. What does the embedding layer look like in terms of the value representation? Is it fixed or changes in values each time? The embedding layer, are you referring to W1 or are you referring to the hidden layer? I'll speak through it anyway. So W1 is a weight matrix. This is just a normal one layer neural network. This is a shallow neural network. And we're using our weights matrix as the embeddings matrix. So in our downstream tasks, we're going to save this weight matrix and we're going to load it in. And this is literally what this Gloves dictionary is, right? So this has been trained on some model. I think it probably was on a neural network. And we've now saved the first weights matrix. And this is what we load in, right? So we have here, this is for the word the. So if we were to, if we had a one hot encoding of the word the, we could multiply it against this dictionary or this embeddings matrix and extract out this same feature for the word the. They look like in terms of the value representation. Okay, so during training, the hidden layer obviously gets updated, but after training, then no, we basically discard the hidden layer and this W2 weights matrix, and obviously we don't really have an output layer That's just a conceptual thing for training the algorithm. So during training, this embeddings matrix gets updated. But what I was trying to say with this this horizontal purple line is that the values in the hidden layer are going to be the vector for where we have a 1, right? So for the word this, the values in this hidden layer are going to be this vector. Okay, so given the context word this and j being 1, we want to maximize the probability that the network outputs y hat to movie. So we want to maximize wt plus j given wt. So how are we gonna, well, first of all, to transform this output to a probability distribution, we're going to use a softmax, right? So what a softmax does is, given a vector, it will basically say this is the most prominent element in the vector, which is the highest number in the vector, and this is going to have a high value, and all the other vectors are going to have a low value. But the whole vector, after it's been run through the softmax operation, the elements of this vector will sum to 1. Okay, and just to make a quick note, in this skipgram model, they were it kind of implies that you're predicting 4 context window times 2 outputs at a size. So in this example, four targets at once. The way we're actually going to implement it is we're going to implement it with using these training pairs that we discussed earlier on, and we're only going to say, okay, for the word this, we're going to train it against movie if that's the current training pair that we're considering, and if we're currently considering the word had, we're going to train it against the word had. And mathematically, the losses will become the same, whichever strategy that you choose to do. So this now frames this problem as a multi-class problem, right? Our input can go to one of multiple classes. And before we actually get to implementing this loss function, I'd like you guys to think about what loss function is used in a multi-class problem. Feel free to leave a comment or whatever, and I'll check it before I give the answer to that. Okay, so the network only outputs one prediction at a time, and we want a loss for all of the J's. We want a loss for all of the context window words for the context word. So we want to have loss for so for the word movie, we want to have a loss for this, had, and a, and this is given by simply doing a sum over the individual losses. So a bit more mathematically now. So for one pair, our probability that we're trying to optimize is wt plus j given wt. So the probability that the word movie appears given that we predict the word movie given the word this, and we want this maximized for all of wt, for all of the j's. Okay, so for all the window words in our context, we want to maximize this, and we'll do that by a product of the probability over those wt plus j words for every j that we have. And we want to do this for all of the words in our corpus, or for all wt in our sequence, right? So this is simply another product for all the words in our sequence, for all the words in our sequence, for all the context words, for the context window words which appear in our context, work out the probability and multiply them all together. So we're going to replace this with a log probability instead for numerical stability, because when we run probabilities over very small numbers, they continue getting smaller and smaller, right? If you think about 0.002 times 0.005, that's a small number, and we want to stop this kind of numerical underflow from happening. So we for implementation purposes we change it to a log, and because log is a monotonic function, we're allowed to do this, and we can apply the log rules to change the products into a summation. And rather than maximizing, we in the neural world, we like to minimize our optimizations. So we want to minimize the negative log likelihood of a window word appearing in the context word parameterized by the parameters of our neural network. Okay, so what is this probability distribution? Well, as I mentioned before, it's a softmax over our outputs. So we can actually represent this as the second weight matrix for the output word times the hidden layer for the input word over the summation for all the words in our V as in vocabulary words in our sequence. Sorry, over all the words in our vocabulary, because our output layer is vocabulary length, where each individual neuron here is referring to one word in the vocabulary. So if you guys recognize this kind of general structure, it's actually a softmax of the output. So our network makes a prediction, or it outputs values for each one of these neurons, and then we do a softmax over all those values, and this gives us our prediction. And this is simply multi-class classification, and it's a very common operation, very common thing we optimize against, and we use an object, or we use the cross entropy loss function to do that. Cool. Just to make you guys aware, so here we have the negative log likelihood and the softmax. Now, if we were to softmax the output and feed this into the negative log likelihood formula, it is the same as the cross entropy loss. And when we actually get around to the implementation part, I'll harp back on that again. Okay. Let's see. Okay, so we'll take a break. We'll do this up to the actual neural network part. We'll take a break, and then we'll come back and finish the rest of the lecture off. Okay, so what we want to do is we want to extract the set of unique tokens from our vocabulary. Previously, we loaded it in an external vocabulary file, but this time we're going to do something which will appear a lot more like what we do in practice in real-world NLP, and that's using our corpus to generate our vocabulary. So let's just print our corpus to remind ourselves of what it contains. Comment this out because this is probably referring to an old variable vocabulary, and I think we want the tokenized corpus because we've tokenized things in there. Okay, cool. So we want to get a list or a set of unique tokens in our vocabulary. So we can do this a couple of ways. I'm going to show you a way using sets, which I think is pretty cool. So vocabulary equals set, and we can just pass in token for token in tokenized corpus. Will that work? No. Okay. Let's break this down. So vocabulary equals set. For sequence in tokenized corpus, we're going to do vocabulary dot add, I believe it is, sequence. On hashable type list, maybe it's update. Okay, here we see that we now have 82 unique tokens in our vocabulary, and the vocabulary is the set of those unique tokens. Okay, what we got to do now is map we're going to have to generate one-hot vectors, and to do that we want to map each of these individual words to an index. We're going to call this our word-to-index dictionary. So for every token in our vocabulary, if the token is not in this word-to-index dictionary, we're going to say, okay, let's have this token as the key of our dictionary, and the value is going to be just some unique counter on it. And we should have the length of the dictionary be the exact same as the length of the vocabulary. But basically what it's saying is now amount is going to be 0, or the value of the key amount is going to be 0. The value of the key what is going to be 1. The value of the key excite is going to be 2. And when we print that, we'll see that, okay, that's what it is. So key value. What this means is that now we can now refer to a word by its index or its integer, as opposed to the actual word itself. And now we need to build our training pairs. Okay, we need to build this. Okay, we need to find a way of getting going from a sequence and extracting out the training pairs. Okay, how are we going to do this? Okay, so just to dive into a bit more codified version of what I'm saying. So considering the tokenized sentence, this movie had a brilliant storyline with great action. For every word in the sentence, we want to get the words which are a window size around it. So if the window size is 2, for the word this, we obtain this movie. Okay. So, and this had. So here, for every token in our sequence, extract window size 2 from it. So in this case, we don't have anything previous, so we just take movie and had. For the word movie, we obtain movie this, movie had, and movie A. And for the word had, we do actually have access to 2 previous tokens. So for the word had, our training pairs are going to be had this, had a movie, had a, had brilliant. And this is the function which will do that. So we take in our tokenized corpus and we define our window size. And we initialize a list which will contain all those, all the values, all the training pairs. So for every sentence in our tokenized corpus, we're going to enumerate over that sentence, taking the token and the token index. And now for every window in our window size range, we're gonna find the context word position, which is the index of the token that we're currently enumerating over, plus W, which is another index because this is a range operator. Now, this line is saying that if this word occurs, or if W, this range, is 0, as in if it's the word that we're currently focusing on. If it is token index, then we're going to skip. If it occurs below 0, so that's here. So if W is like these non-existent words here, we're also going to skip. And if it's greater than the length of the sequence, so if it's words here, we're also going to skip here. So we do that, and we obtain our training pairs. So you can see we actually have quite a lot for a short corpus. Yeah, vocabulary isn't a dictionary. Vocabulary is a set. So all we want to do is make sure that the words index dictionary contains the same number of elements as our vocabulary. As the words index dictionary should be containing a key for every single word that it is in our vocabulary. So yeah, you're right that it doesn't validate the dictionary keys of them, but the point is just to make sure that it has been populated to have the same elements as our vocabulary. Okay, and using the word to index dictionary that we just generated earlier on, we're now gonna enumerate all of these or integerize all of these. And we're just going to do that by creating another. It's going to be a list of lists, as this is, where every sublist is going to be the indexed version of that word that appears. Okay, and just for a bit of a sanity check, so the first words are this movie, this has an index of 12, and movie has an index of 59. So if we look at our vocabulary, index 12 is this, and index 59 is movie. Okay, so we now have a correct focus context index pair list. And we need to one hot. I think this is going to be called in our train loop. Okay. So what we're going to do is we're going to take in some indices, and we're going to define the length of the vocabulary size, which is obviously, if we refer back to this first picture here, or not the first picture, but this picture is going to be it's not 10,000 in this case, but it's going to be how big we want each individual vector to be. Oh, sorry guys, my laptop isn't charging. I just want to figure out why. Okay, so we have our one hot matrix, which is going to be the number of indices in our sequence, and each sequence element is going to be of vocab length size, and for every index in our list of indices, we're going to assign the relevant value in our one hot matrix to be 1, and then we're going to return it as a tensor. Okay, so we're just going to have some torch imports that we're going to use, and I want you guys to take 10 to 15 minutes to code up this neural network. Think about the answer to this question: why we don't have an activation function in between the input, or in between the projection and the output. So what you guys need to do is code up these two things, and Oh, actually, that looks like it's it. So yeah, I'll give you guys till 40 past, so about 8 minutes to do this. Oh, you might have to look at the reason I'm giving for so long is it is only 2 lines that you have to fill in, but you might have to look around at the PyTorch documentation to see what we need to put here. So remember, these are just layers of a neural network, and that's the hint that I'm giving you. Okay. Let's continue. Okay, so our projection layer is just going to be a normal linear layer. So nn.linear, and we're going to take in input size, and hidden dim size is going to be our embedding size. Okay, so embedding dim equals hidden dim size. That makes things a bit easier for you guys to understand. Okay, so what this means is that our weights matrix, this is what we're referring to as W1. So we have a hidden layer, which is E size, embedding dim size, and our input layer, which is V, or vocab size. So our weights matrix is going to be V times E. It's going to be vocabulary size down and embedding dim across. And from our hidden layer to our output layer, we're going to have a E times V matrix. And what this is embedding size down and vocabulary size across. I now just realized how this would make sense if it was a bit shorter, but yeah. So embedding size down and vocabulary size across, and that's going to be the transformation that we apply from our hidden layer to the output layer. And so to do that, we have nn.linear, and we take an embedding dim and return output size. Guys, while I run through the rest of this code, can you put in your suggestions as to why you think we don't have an activation function in between the hidden layer and the output layer? Okay, and this is just because TensorBoard doesn't support handling emojis. I didn't actually answer this question earlier on, but we don't really need to do anything to emojis because they do count as they are an atomic unit of a sentence. So we can just process them as is. And up here we have a, what the Unicode representation of an emoji is. So this laugh emoji is represented by the Unicode 128514. And because TensorBoard doesn't support this Unicode encoding, we need to just rename the Unicodes that we have in our word-to-index dictionary with something which is 1, human readable, and 2, understandable by TensorFlow. So that's all we're doing with this line of code, or this block of code. As far as our just to finish off this the Word2Vec model. Our forward pass is literally just going to be passing the input token, the one hot input token, to our projection layer or our hidden layer. And then the output of this is passing this X into self.output, which will give us the logits, which we then run the cross entropy loss over. And the cross entropy loss, which we define here, is a softmax followed by a negative log likelihood. And we can see this if we look at nn.cross entropy loss. Okay, this criterion combines log softmax and negative log likelihood into one single class. And to answer that question that somebody asked earlier on about what base the log is in, let's look at what log softmax does. And applies the log of softmax x. Okay, this doesn't say, but because it says this log, I imagine that, I don't think there is probably in the functional. Yeah, I took a look at the documentation while we were on the break, and the log said it was in base E. So I imagine this log here to be in base E, and thus the cross entropy loss to be in base E. Okay, and we're going to use a simple stochastic gradient descent optimizer. So for all of our index pairs, we're just going to randomly shuffle them, and we're going to loop over them for the amount of epochs that we have. So for every focus context pair in our index pairs, which is, for every focus context, focus context, focus context, focus context, we're gonna get one hot of our focus word. Then we're gonna initialize the target as just a tensor, and we're gonna use the Word2Vec model that we pass in to generate our predicted outputs, or in this case our logits, and that's obviously just this return output here. We're then going to feed it into the predicted outputs into the loss function with our targets, and we're going to backprop and optimize and zero out the gradients, and we're going to save our models, and I'll show you why we're doing that in a second. I think you guys will find this really cool. So we'll train this. Okay, and now we're going to run TensorBoard. And what TensorBoard allows us to do, so to run TensorBoard, type in, navigate to your word representations directory, and do TensorBoard -dag logdir equals runs /Word2Vec. And let's head to localhost. And this is a really, really cool feature of TensorBoard. We can visualize our word embeddings in projected down to three-dimensional space. So our word embeddings that we did here were Word2Vec 10 dimensions, right? Our hidden dim size is 10. Using statistical linear algebra, using just linear algebra, we have methods to project vectors in higher dimensional space to lower dimensional space, and this is what TensorBoard is doing here by projecting our 10-dimensional vectors to 3 dimensions and assigning them into our and putting them into this 3D graph. So we can see here that words which we would expect to be similar, so like brilliant, don't really come up with words which are similar to it. And two words which should be similar, like movie and film, should be similar to each other, right? But in this context, they're not. And the reason for this is literally as simple as we just don't have enough training data. So what we're going to do now is we're going to look at Spacey, and we're going to look at a larger corpus of training data, and train our model on this larger corpus, and then show how that our algorithm is actually functioning correctly. Values in the embedding are within the range of the domain and subtext. I don't fully understand what you're saying. We're doing a softmax to have a probability distribution on our output because this is what we're going to optimize our loss against. We can't optimize against the raw logits. Oh yeah, it's well cool, isn't it? Okay. Okay, so we saw some issues that using like albeit primitive, but our rules can cause for pre-processing. And, sometimes it might just take too long to code up, all the rules for every edge case. And we might also want to augment our data with some more information as well. For example, a parts of speech tag, which has an identifier per word, which describes what type of word it is. So, for example, a verb or an adjective. So Spacy is a NLP library, which is very easy to use and gives us access to neural models, which allow us to have these kinds of various linguistic features. In this section, we're gonna use the tokenizer to pre-process a lot bigger and a lot larger corpus of text, and then train a Word2Vec model in this corpus. And then I'm gonna show TensorBoard again and show how that show that the very same model, this very same model that we just coded up, can represent, does actually work, and we can show the similarities and analogies working in there. So we're just gonna load in some imports. This is the important one. NLP equals spacy.load.en, and en is the language model which I asked you guys to download earlier. Okay, so we're gonna use this corpus called the Gutenberg books, and these are basically just popular books which are now copyright free. And I'll just show you an example. What's the smallest one? That's a README here. Here we go. So it's just a text file of a book. These are just help functions, and all they do is load the books into our kernel. So all we're going to say is we're going to only consider 3 books, and then we're going to split the books on new lines, just so we have a list of sentences. I would print this, but it will just take too long to print. So just trust me that we have. Actually, what I'll do is I'll print 0, 0, and that should. So that gives us. The first sentence of the first book. This is the second sentence of the first book. This is the third sentence of the 33rd sentence of the second book. Okay. Now, for every line that we have in this Gutenberg book lines list, we're going to tokenize this. And how we're going to tokenize this is we're going to lowercase it, and then if it's not a punctuation either, we're going to for token in doc if not. Okay, we can't lowercase a sorry, we're just going to omit the punctuation as well. Now, running this takes way too long to do it manually, so I've tokenized it for us previously, and we can just load that in. No, I'll go in a bit. And this will give us our tokenized corpus. So let's try and print this and see what it is. Just do can't remember off the top of my head, so okay, yeah. So it's going to be all the tokens in the first sentence, all the tokens in the second sentence, or third sentence, I should say, and this should go up to like some ridiculously high number. So just print the length of this, and we'll see how many sentences that we have over all the books that we're considering. 109,057. Okay, so one thing that I didn't mention previously was the discrepancy in the words which might be present at test time and at inference time, as in when you want to deploy this model, but those words not being present in the training phase. And these are known as out of vocabulary tokens. A simple strategy that we used to deal with this and is still used in NLP is just to replace every word in our training set which occurs less than a certain threshold of times with a special outer vocabulary identifier. And that's a token. And at test time, if the given word isn't in the vocabulary that the model was trained on, all we do is we just simply replace it with the outer vocabulary token. And here we're defining this threshold to be 5. So any words that occur less than 5 times, we're going to replace with this outer vocabulary token. And just a bit of code for us to do. Okay, so let's read through this function. So we're going to pass in our tokenized corpus and the frequency, the threshold that we want to cut off under. We're going to initialize our vocab frequency dict, which is going to be a key, a dictionary, where the key is the word and the value is the frequency that it appears. So for every sentence in our tokenized corpus and for every token in our sentence, if that token does not appear in the dictionary, then we're going to add it to the dictionary and we're going to initialize it as 0. If it has appeared in the dictionary, we're going to add 1. Okay? Well, not if it has appeared, then we're just going to add 1 anyway. So we won't see the word will be in the dictionary on with a value of 0. And then we're going to have this next line, which is going to add 1. So that means we've seen this word 1 time. Okay, then we're going to have our vocabulary as a set. And for... let's see what the code is. A bit intimidating to do it live, if you know what I mean. Okay, so for every sentence in our tokenized corpus, for every token in our sentence, gonna add that to if the frequency of this word token is greater than cutoff frequency, so greater than 5. So if we've seen this word more than 5 times in our corpus, frequency, then we're going to add it to our vocabulary. Vocabulary.add token. And I don't think we add the... Okay. And then we return this vocabulary. We run this, might take a second, but we see that the number of unique tokens that we have is 8,447. Okay, now we're going to replace, for those words which have occurred less than 5 times, we're going to replace them with an outer vocabulary token. So we're going to add the outer vocabulary token into our vocabulary, and then we're going to initialize our word to index dictionary. So for every sequence or for every sentence in our tokenized corpus, for every token in that sentence, if the token is in the vocabulary, we're going to add that token into this list. If it's not, we're going to add the outer vocabulary token in there. And obviously, this else statement is only going to be triggered if the word appears less than 5 times in our corpus. And then we append this outer vocabulary sentence to the outer vocabulary token list. Okay, and now we're going to populate our word to index dictionary. And we're going to use the get focus context pairs function that we defined earlier on to get passing in the tokenized corpus to get our focus context pairs. Yeah, hey, sorry for pushing this back a bit. We thought if we started at 7, it would end quite late, and that's not something that we wanted to do with on a Saturday. And I think there was also miscommunications in the timings between me and one of the other members of the team. So we started it a bit earlier today, but we'll have a video uploaded shortly after this lecture. I'll get on that straight after it's finished. Apologies about that, guys. Okay, so we have the focus context pairs, and we see that we have a lot of outer vocabulary tokens in the very first part of our corpus. Now we're going to get the index pairs. While that's running, we'll just initialize the summary writer, and we will have our new Word2Vec model, which is the length of this vocabulary as the input, length of the vocabulary as the output, and again with 10 dimensions. And then we're going to train it, and we're going to early stop because this will take way too long to train just on a CPU. So we'll just do one epoch, and we'll break. I think that's broken. Okay. And now what we're going to do is we're going to run TensorBoard again. And we're going to run it instead of in the Word2Vec directory, we're going to run it in the Word2Vec Gutenberg directory. And this is going to have a model which I have pre-trained using exactly the same code that we've just run through. So I've just used this code, stuck it in a Python file, and trained it for 10 epochs. Okay, cool. So we obviously see a lot more points, and that's because we obviously have a lot more words in our corpus. Now let's look at some of these words and see what we can find words which are closest to. So let's just start with king. Sorry, it's a bit laggy. And we see, okay, so king is very related to elders, rulers, soldiers, inhabitants, and these are all kind of like, you can imagine these being basically viable things which are close to king. Other things might be, guys, if you have any suggestions of things you want me to try out and stick in here, then feel free to do so. Otherwise, I'll just click on. Let's find a random word to click on. Furniture. Okay, so for some reason we see killing in the context of furniture, and actually this is one of the books that this was trained on is the Bible. So I can imagine there to be lots of words appearing in very interesting contexts. But we can see generally that even with this small dimension, we're only training on 10 dimensions, and it is a relatively small corpus. Like most of these pre-trained models are training on hundreds of thousands, if not millions of data points. We can see that even with this relatively small corpus, we are getting things which somewhat make sense, or a lot more than what we did with the toy movie reviews dataset that we were working with. Okay, so lastly is how do we actually use these word embeddings? Well, our word embeddings are the projection weight matrix that we trained earlier on. So the weights of this layer is our word embeddings matrix. So what we need to do, we simply just take this layer and we can save it, and we can pass it to wherever we're doing a downstream task, and our neural network will be initialized with these word embeddings. And as you can see, the weights matrix is of shape vocab size times hidden dimensions. guys, that brings us to the end of this lecture. Once again, apologies for pushing it back a couple of hours. If you keep your eye on Eventbrite, I think when Harry comes back from the shop, me and him will discuss when we want to run our next NLP session. I imagine it'll be at 1 o'clock next Saturday, but keep your eyes peeled and we'll update you over Twitter, Instagram, Slack, whatever, WhatsApp, whatever community you're part of, and email, obviously. If you've got any questions, I'll be here for another 5-10 minutes or so. Then feel free to ask them. Otherwise, you can always catch me in the Slack or WhatsApp group. Again, thank you for being here, guys. I appreciate taking time out of your Saturdays is quite valuable. I just thought I'd come back and answer these questions verbally instead of typing them out. So would be great to see the values of the weights layer and hidden layer as well. Also have an indication like base of function x is ABC, like in the case of log. Personally, I want to say that I don't think the base of the log is too important in this context. It's there for two reasons. One is the monoticity of the function, and the other is that we can apply the log rules to remove the product and actually have a summation. And these are consistent over all the log bases that you use. So as long as that base is consistent for the task at hand, then I don't think what base it actually is too important. As for the first point that you mentioned, the values of the weights weights layer and hidden layer, yeah, that's an interesting point, because the glove vectors that we loaded in, so this is the hidden layer for the word the, right? All that's going on in Word2Vec is that because we're feeding in a one-hot encoding, because our input is one-hot and we have this weights matrix, the value of the hidden layers are this vector where it's 1. So let's say this is 10,000. That means that this, and our hidden layer is 50. That means that our weights matrix is going to be 10,000 down and 50 across. And where our input is 1, so in this case this, so where it's 1, so for index 7,500, let's say, we're going to look at index 7,500 in this weights matrix and have this vector. And that will be this vector in the hidden layer. Because what we're doing is we're timesing a one-hot vector by a matrix, and all that does is extract out the relevant vector for where the index is 1. As for the second question, in the skipgram model for a phrase like I think this movie, if WT equals these and WT minus 1 equals think and WT plus 1 is movie, and if you want to predict the next word that follows WT these, how do you avoid that you get the previous one? This is a very good question, actually. So in this case, you don't. You say, here is the word, make a prediction from this word, and looking at t equals 3, right? Just because it's got the most examples there, or the most pairs there. Your network, your ground truth is most likely going to be one of these words. But let's say your ground truth is movie, but your network predicted brilliant. Now, your network is going to optimize to say, oh, well, actually, this prediction was quite far off. We actually wanted the word movie, so let's move our weights closer for the input word had, closer to predicting the word movie. Now, the point is, over time, we're gonna collect so many of these training pairs, and we're gonna have so many focus words, so many of these WT words, that the optimization process essentially becomes an average over all the context words which appear in context of that focus word. So we don't want to restrict it to only look or only optimize for the words ahead, if that makes sense. Guys, I'm gonna call it a day here. I'm active on the Slack channel. I think the link for that is on our Instagram. If you want to join in and drop me a question on there, then I'll be more than happy to respond. I'll get Christian to send out an email with the VOD after I finish uploading it, and I'll also post a link on the Slack channel about that. All right. Thank you guys for joining, and once again, apologies for pushing this session back by a couple of hours.